in the XY plane. It doesn't have to be a rectangle. So this says write a double integral expression that gives, and this is a new piece of notation for us. So last time, because we were only dealing with rectangles, we were always able to write from x equals this, x equals this, y equals this, y equals that. But sometimes you can't write it in such a way that looks like that. So we're going to say a double integral expression and then using a subscript over the region R. And notice it's a little mysterious as to is this dx or is this dy. So they're going to call this kind of a dA, which is dx times dy. You could think of it as like a change in some area. So this is your general notation for saying the volume underneath the surface over this region R. And R even could be a rectangle. And then they will give you a description of what R is. It's either a verbal description, it's either written in inequality, or I could just print out the actual graph in the XY plane and you would be responsible for figuring out what R equations for R. So it gives me a verbal description. It says R is the region in the first quadrant bounded by square root of x and x equals 9. I will let you know today's lesson is only interested in the region itself. So don't even worry about, they didn't even tell me what the surface is. All we're doing today is worrying about just the region in the XY plane. So it's going to feel very familiar. It's going to feel almost like what we were doing in Calc 2 when we were finding areas between curves. So it says it's the region in the first quadrant. First thing I'm going to do is just sketch the first quadrant. It says bounded by square root of x. So I'm going to go ahead and sketch that. And x equals 9. So this is R. And although yes, square root of x drops down forever, x equals 9, you could have had everything to the left forever. It does say in the first quadrant. So you know I am bounded by both x equals 0 and y equals 0. So that is the region that I am integrating over. So we're looking down, this is our xy plane. And imagine there is some sort of surface floating over R. And we are going to find the area, the volume between the xy plane and your surface. The question is how to write a double integral expression. And this is exactly, feels very familiar to something we were doing in Calc 2. So looking at the region R, we're definitely integrating from x equals 0 to x equals 9. That part is clear. And I can't really integrate all the way from y equals 0 to y equals whatever this point is. Plug in 9, square root of 9, you get 3. Because if I integrate from y equals 0 to y equals 3, I'm just getting this entire rectangle. So what this is saying is you can integrate from the bottom curve to the quote-unquote top curve. So if you want to imagine drawing like a vertical line, and again, this will really start to feel like things we were doing in Calc 2. Then I get that my bottom curve is the line y equals 0 all the way up to my top curve, which is y equals square root of x. So one way you should instantly be reading this, a common mistake is people always want to put, this is going to be in terms of x, square root of x. They always want to put dx here. But careful, this should make sense. This is y equals 0 to y equals square root of x. You would not say x equals 0 to x equals square root of x. So that means this over here, a and b, are going to be constants, and we're sweeping left to right, so from x equals 0 to x equals nothing. What is the surface f of x comma y? Don't know, we don't care. This lesson is only interested in writing an integral that gives the volume. If this was something like, x plus 3 or something, then using our iterated integral techniques from last time, we could then find the volume. Please ask questions.
Well, I'll look in that line, like first y, then d.
And we will do this too today. Let me go ahead and just show us what this region looks like. So I'm going to go ahead and, for Desmos purposes, I have to sketch some general region. So I'll just put cosine x, cosine y, plus 5. Sure. So this is the surface, but I only want the volume underneath the surface over region R that we sketched there. So it's not going to be too bad. You're going to say, draw the surface, f of x comma y. Let's switch that. And if you can write the double integral expressions, having Desmos sketch this comes pretty naturally. Because in your curly braces, you're just going to write that y is going from y equals 0 to y equals square root of x. So in my curly bracket, I'm just going to put y is between 0 and square root of x. And you can kind of see Desmos is going to sketch this now, kind of going all the way out. And then just put another curly brace. And you're going from x equals 0 to x equals 9. So right now it's sketching just the region R, but I want the volume underneath that surface. So I'm actually going to say, that z is between 0 and the function. One more time.
Might be a little too high because when I was showing up, there's just.
I had it before I walked up, so let's see how it works. I think I see. If we don't put it in curly brackets, and then just put the restriction. There we go. So for your inequality for Z, don't put that in curly brackets. That is the thing you're sketching over these regions here. So you can see, looking down in that bird's eye view, you see region R that we're talking about. And you could change your function to be anything. If you just want Z equals 6, then you get a flat plane there. If you want it to be X plus Y, have kind of a slanted plane. Or again, if you want kind of the cosine, you want those like wavy aspects to it. All right, let's try some more. So write an integral expression for, again, our new piece of notation. This is saying the volume underneath the surface G over the region D. dA, it's not telling me the order of integration. And it's saying D is the region bounded by y equals x squared and y equals 2x plus 3. Again, all we're interested in today is just the region itself. So I'm going to go ahead and sketch my region. I've got y equals x squared, I've got a parabola. Now I want the line y equals 2x plus 3. That's a straight line. Positive y-intercept, positive slope. So I'm going to give you guys a couple minutes, talk amongst yourselves. It's just going to follow the same format. You're going to go from the bottom curve to the top curve. That doesn't feel that bad. The only thing is, it's unclear sweeping in the x direction where to start or to end. It might just take a quick few seconds of algebra to figure that out. From here to here. How would I find those x values? You could, but I feel like you can You got this.
Oh, yeah, I think that's right. I think it's like factor.
Mhm. So you have the x values, and you know y equals x squared, and y equals 2x plus 3. Well, since they're equal to each other, they intersect. Gives you the same for both. So it does not matter which one you plug in. So to find the x values, I want to find the intersection of these two curves. A good question is, can I just find the intersection point by graphing on Desmos? Sure, we have a section of the test that is open resources and Desmos. I have no problem with that. But say something like this shows up in the multiple choice, we should be able to do this part. So starting, it says from bottom curve to top curve. So again, just to help my brain stay organized, you're always gonna see these sketched just like a general vertical line. The bottom curve is y equals x squared, so that's the bottom bound of this innermost integral. Going all the way up to y equals 2x plus 3. So that part wasn't that bad. This algebra technique was the only thing we really needed. And then sweeping in the x direction from x is -1 to x equals 0. Please ask questions. There's one more interesting thing that we can do here. So I keep saying that we're going to find the volume underneath some general function g. Again, for today, we're not interested in what that is. But what if instead, I don't want the volume underneath this region D, but if I want just the area of region D? How could I still keep a double integral expression, but find only the area of D? So part B is write a double integral expression that gives the area of D. So I'm thinking, okay, to find volumes of things, it's always going to be the area of the base times the height. Well, if I want just the area of D, then you can kind of treat it like a volume, but just make the height 1. So it's going to be area of the base times, if you just make the height 1, you just get the area of the base. So your trick or your technique for finding the area of a region is you can do the definite integral using the same limits of integration, but just make the integrand 1.
That applies to every time you get this question?
Correct, yes. And you might be thinking, well, hang on. When I was in Calc 2, though, we always learned that the area of a region between two curves, you just did the top curve minus the bottom curve, and then you integrated from A to B. So how on earth could this possibly be the same? And I will show you that they actually are the same. If we wanted to use our iterated integral technique, I'm going to take the antiderivative with respect to y, which is just y. Plug in the top curve minus plug in the bottom curve, and notice something I stumbled on. I actually stumbled on the form from Calc 2. So they are equivalent. So there are ways of writing double integral expressions that give all of the areas that we were always finding in Calc 2. You're just going to treat it kind of the same way that we're finding the volume, just make the integrander 1, and you're going to end up with an area. Have a rocket. So this says, let this surface equal e to the xy squared. Let R be the region in the first quadrant bounded by y equals x and y equals cubed root of x. So you'll notice kind of one of those parts where it says use technology. So we're going to say that this is a Desmos question. So maybe I don't remember